Hello and welcome to SAP TechEd 2021. I'm Vahid Bisadi and I'm a senior data scientist at SAP CX AI Group. Today I'm going to talk about the use of AI to detect real-time intrusions in web-scale authentication systems. Here is a brief agenda of my talk today. First, I'll go over introduction and problem statement. Then I'll talk about the solution architecture and machine learning model. And at the end, I'll go over the results, conclusions, and future work. Here is a brief overview of SAP Vision for Intelligent Enterprise. As you can see, it has several components like business process, applications, technology, and infrastructure. And the topic of this session, it fits under infrastructure because the technology that we are developing will be plugged into hyperscaler and will be used by SAP customers. What is an intrusion detection system? Intrusion detection is the process of monitoring and analyzing the events occurring in a computer system or network for signs of possible incidents. Incidents could be violations or imminent threats of violation of computer security policies, acceptable use policies, or standard security practices. This talk presents an innovative and adaptive AI-based approach to detect intrusion incidents on a very large scale in real time with maximum capture rates, leading to improved user experiences and customer satisfaction. There are three categories of traditional detection methodology: signature-based detection, in which we define a signature for the normal behavior of the user, and then for login attempts, we compare the characteristics of those login attempts with that signature to detect if there's any intrusion or not. Anomaly-based detection algorithms, in which we use some anomaly-based methodologies and algorithms to find anomalies in the data and find intrusions. And a stateful protocol analysis, in which we run some analysis to identify deviations from a protocol state. But modern detection methodologies are based on AI because AI-based methodologies provide a fast and efficient solution to find patterns in dynamic systems. Here you can see an overview of 1 week of login attempts on SAP customer data cloud solutions in the United States on the top graph. And at the bottom graph, you see the highest peak in the United States, which lasted for about 12 minutes. And as you can see here, during the peak time, we need to process about 800 login attempts per second, which needs a very fast algorithm to process that. And here you can see the same graphs for the European Union. And here you can again see that during the highest peak in the European Union, we need to process about 700 login attempts per second. So these graphs illustrate the dynamic nature of the problem and the need for a fast intrusion detection system. Here you can see invalid credentials versus successful accounts login rates. And as you can see, invalid credentials constitute the major portion of login attempts in SAP Customer Data Cloud solution. And you can see that about 88% of the login attempts are from invalid credentials, and it can be expected because normal users usually try a few times to be able to successfully log into their accounts. And because of that, we need a powerful intrusion detection system to prevent harmful consequences. And here you can see top user agents with invalid credentials. As usually attackers, they try to mimic what normal users do. Therefore, we need an adaptive and fast AI-based intrusion detection system to detect the intelligent behavior of attackers. Traditional intrusion detection systems that are usually rule-based or heuristic-based and static, they won't have the ability to detect the complex and intelligent behaviors of attackers. Here you can see the solution architecture we used for this problem, and we have some clients that log into the SAP Customer Data Cloud, and you can see the CDC in blue rectangle here. And inside that, we have microservices and Apache Kafka. And CDC, it sends some queries to the risk assessment providers module. Inside it, we have the two-factor authentication provider or CAPTCHA provider, and also we have a machine learning module. And the machine learning module includes the REST API, and it uses it to communicate with the CDC and risk profiles and ML model. And the ML model, it calculates the risk score and it returns it back to CDC system. And based on that risk score, CDC decides if further security actions are needed or not. And the ML part of the system is implemented in Kubeflow and Apache Spark to serve the scalability requirements of the system. This session is focused more on the machine learning and data science aspect of this project, but if you are interested in architecture, engineering, and production aspect of this project, of this problem in more details, please watch ISP 205. So to create a machine learning model, the first step was that we selected some candidate models in two categories. Supervised models that are models that need labels based on ground truths for training. And in that category, we tested a gradient boosted decision tree and a deep neural network. And another category is unsupervised models. Those are the models that do not need labels for training. And in that category, we tested a simple heuristic model, an isolation forest model, and one class SVM. And we did several preliminary analysis using these candidate models, and it showed that the supervised methods provides better results in terms of finding attacker IPs. And among those models, gradient boosted decision tree provided the best results. Here you can see how we generate the labels for supervised models. We consider a 15-minute rolling time window, and for each user or IPM device, we develop some features that I'll talk about them in the next slide. But for generating the labels, the success of the last login in the 15-minute time window is considered as the label. And the model is trained to predict this label given all of the features from the previous login attempts. So basically what this model does is that it tries to predict if the next attempt of the user would be successful or not. And based on that, it generates a probability of failure or risk score for that user, and it sends it back to CDC system. For the features, on the left-hand side here, you see the categories of features we use for each user, and those are temporal features, spatial features, historical features, and technical features. And on the right-hand side, you can see some samples in each category. And due to brevity and security reasons, I haven't put all the features we used in the model here, but you can get an idea of what type of features we use. And also, as a future work, we are planning to add behavioral features like the movement of mouse or the duration of time between mouse clicks to add to the model to improve the precision of the model. So machine learning model, it has two phases, the training phase and the scoring phase. During the training phase, the first step is that features are built from recorded events using a rolling time window, as I explained before, and then model is trained with the constructed features once we have them. And then for unsupervised model, the goal is to discover the anomalies in the data given developed features. For supervised model, the goal is to predict whether the next attempt of the user will fail or not. And in addition to that, we also have a grid search optimization algorithm that is used to find the best set of hyperparameters for the model. During the scoring phase, the first step is very similar to the training phase. Actually, it's just developing the features similar to what we have in the training phase. Once we have the features, we can pass it to the train model to estimate intrusion probability. And once we have the scores at the last step, we send those scores back to the CDC system, and CDC decides if there's any more security actions are needed according to the scores. To evaluate the model, we use the popular metrics of precision and recall to evaluate the model. Precision in general is defined as the true positives divided by predicted positives. In this problem, it represents the proportion of predicted attackers that are real or actual attackers. And since that tagging IPs as attackers has some consequences for the corresponding users, such as blocking their IPs, we need very high precision to avoid blocking normal users. Recall in general, it's defined as the true positives divided by actual positives. In this problem, it represents the proportion of all real attackers that are detected by the ML model. And since not finding an attacker leads to their possible harmful actions to the system, we need a high level of recall as well. But to evaluate the model, we need a single metric, and we need to combine precision and recall. So for that purpose, we use the F-beta score, as you can see in this formula. For F-beta score, if we want to put more weight on precision, we need to choose a value of beta less than 1. But if we want to put more weight on recall, we need a value of beta higher than 1. In this problem, because precision is a little bit more important for us, we decided to use a value of beta equal to 0.5. And so we used F.5 score to evaluate the model, and it's used for hyperparameter tuning and checking the quality of the model. And here you can see the results for a sample of data streams from CDC system. We could get a precision of 96%. It means that among all the predictions of the model, 96% of the cases that the model predicts they are attackers are actual attackers. And recall, we could get a recall of 90%. It means that the model can identify 90% of attackers. And we could get a F.5 score of about 95%. We also evaluated the model with AUC score, which is the area under ROC curve. ROC curve is, as you can see here, is when you plot the true positive rate or recall versus false positive rate or fallout. We call it ROC curve, and the area under that curve is defined as AUC score. So a perfect model, it has a AUC score of 100%, but in this case, we could get a very good score of 98.5%. And these are the conclusions. The AI-based intrusion detection system developed by CX AI group is a fast, adaptive, and a scalable system that provides a solution to the increasing need to detect cyber attackers. Developed AI-based system detects attackers better than the traditional heuristic-based system. And as a future work, we are planning to add behavioral feature to the model to improve the performance and precision of the model. So that concludes my presentation, and I wish you the best in your learning journey at SAP TechEd 2021. If you have any comments or questions, please feel free to contact me at vahid.bisadi@sap.com. Thank you.